just test the microphone. Can you speak?
Hello? Hello?
Okay. Yeah, we can hear you just fine.
Okay, so today I'm going to continue to explain to you this the ideas of the resolution of singularities for vector fields in dimension 3. So last time I told you about this invariant, which is this vector of natural numbers. And the idea is that this should be something which decreases after the blowing up. But of course, as I said, it's have to be careful because if you so these are numbers which are computed with respect to the Newton polyhedron written with in some system of coordinates. But the problem is that when you yes, of course, this is far from being let's say an intrinsic object which is associated to the foliation itself, and it's more important. The problem is that when we blow up with the strategy which is determined by this invariant, in principle you can have this problem of compensation, which leads, let's say, to the situation where the invariant does not decrease by blowing up. In this case, it can even increase if you're not careful. Okay, so I just recall to you this invariant. So it's something which is related to the face of the polyhedron and to some vectors which are computed by taking this this edge and so on. I'm going to make a picture in a moment. Okay, so the strategy consists in blowing up with the face which is determined from the main vertex and from the main vertex of the derived polygon. So recall to you, it's a polygon that we obtained when we cut the polyhedron at some height, which is the height of m minus 1/2. Well, so this is yeah. So I'm going to skip this. Yeah. Okay. So I said to you that the one important issue here is to control, let's say in a nice way, the freedom that you have to choose coordinates. And in the two-dimensional case, this was essentially controlled by the fact that you asked your coordinates to be adapted to the divisor, in the sense that the divisor should always be given by, let's say, x equals to 0, where x was one of the coordinates. But in this case, in this high-dimensional case, you have to, in fact, introduce this additional structure, which is called an axis, with, well, roughly speaking, is just another foliation, which it's one-dimensional and is generically transversal to the vector field itself. So this essentially this vertical axis here, and which cuts the nilpotent locus of the initial foliation by, let's say, in a generically transverse way. So in fact, this will control in some way the way that you can choose the coordinates to compute the invariant. So I showed you that you can always find this. So you can always find these coordinates, this x. And now, well, I'm going to talk about this, what we call an adapted local chart. So you have now this 4 data here. So the manifold, the divisor, the foliation. Oops, sorry. And then there is the axis now, which is also part of the data, right? So an adapted chart is something which you will take into account this 4 data here. So, but we also have to fix, let's say, an enumeration of the components of the divisor. Okay, so it also depends on a tagging of the components of the divisor. So I'm going to associate a number to each irreducible component. And this number, in fact, will record the year where this component has appeared in the resolution process. Okay, so let's say the largest number corresponds to the divisor which has been created the latent. Okay, so given this tagging and all the preceding data, a local chart is adapted if, so I want that the axis is given by, let's say, the vertical vector field, d over dz, as in the picture that I mentioned before. So if at the point P, you have one component of the divisor, then it should be given in these coordinates by x equals to 0. Okay. And if you have two components of the divisor, then let's say these components are di and dj with I greater than j. Okay. So it means that, let's say the component di appeared in the resolution process later than dj, and then they should be, let's say, defined respectively by x equals to 0 and y in y equals to 0. Okay, so it means that the divisor x equals to 0 is always younger than the divisor y equals to 0. This will be important. Yeah. Okay. So this is the definition of adapted chart. So I claim that when you ask all these conditions, in fact, you have something which is quite rigid in the sense that if you write the system of, let's say, a coordinate change between two adapted local charts, it has to be has to have this form here. Okay. So so I mean that so in the first two coordinates, x and y, it's there is no dependence on the third coordinate, and then well in z prime can depend on all the coordinates. So this is let's say the case where the point the coordinates are centered on any point on the, let's say, on the manifold. But when you have a point which is on the divisor, you have even more rigidity. So if this point has there is one component of the divisor through this point, then in fact you have this x which factors out on the first map, and if you have two components, then f should be divisible by x and g should be divisible by y. Okay, so to guarantee this, of course, you have to keep track of the tagging of the divisor by saying that x prime and x correspond always to the same divisor. So there is no possible exchange here between these two. Yes, there it is. Well, so well, this is quite easy to prove this because, in fact, by the requirement, so this is the point where we use the existence of this axis in an essential way. So by the requirement that the axis always corresponds to, let's say, to the vertical axis at each point, it says that when you make this change of coordinates, it should map the vector field. So this one, right, to a multiple of this one, right? So this implies immediately that the z prime, sorry, that x prime and y prime cannot depend on z. Okay. Well, and then the other two. So this also always already takes care of these two ones. And then, of course, if you ask that the divisor is preserved, then these two other conditions are also easy to verify. Well, so from now on, I only talk about this adapted coordinate system because this is let's say, the setting where we're going to try to compute things, compute this invariant in particular. Okay, so now I recall that you have this adapted coordinate systems, and you have this the main phase, which is both f, and then you have these two vectors delta. Let's say this number delta and c, which in fact they define together with m the affine hyperplane which supports the main phase, right? So there's these three configurations here, and in fact let's say the affine plane which supports the main phase is given by f plus some convex combination of delta -1, c -1, 0. Okay, so now I'm going to take the set of all convex polyhedra of this type, which have a fixed delta m and a fixed delta and c, right? So of course, this polyhedra, all this polyhedra does not necessarily have the same face, the same supporting face F, but in this class, I claim that all of the polyhedra in this class have the same main vertex and the same displacement vectors delta and c. Okay, but eventually, of course, the support of the intersection of the polyhedra with this affine plane could be different. Right. So now I'm going to define a group, which I call the group acting on the face. So this is in some sense a particular case of the group of changes of coordinates in adapted that I've shown in a moment ago, which are just polynomial changes of coordinates which have this form here. So they are triangular and x, y, and z. Okay. And moreover, I ask that these polynomials g and f respect the quasi-homogeneous graduation determined by f. Okay. So what I mean by that? Okay. So I mean, well, I have the stagnant conditions, but essentially means the following that. So in this phase f corresponds, the choice of this phase corresponds to attribute some weight to, so some quasi-homogeneous graduation to the variables z, y, and x. And what I'm asking here is that the polynomial g, sorry, which appears here, has the same weight as y, and the polynomial f has the same weight as z. Okay, so these are the conditions. Well, I can make this more precise. It means that if you take the support, so you make them, you look at all monomials which appear, for instance, in the polynomial f. So all these monomials should be of this form, okay, of the form a and b, which lies on this set here. And well, so they're the case where the first displacement vector is zero, is non-zero, is positive, then it's particular. I'm going to show you a picture. And g is the same thing. Okay, so g is a polynomial only on the x variable whose support should be of this form. Okay. Well, so we have to imagine this as some way of sliding the monomials along the face. Okay, so these arrows that I show here show the way that, let's say, the monomials which are supported on the face slide by this change of coordinates, right? So it means that the graduation, when you say that the graduation is preserved, it means precisely that you have this kind of behavior where the contribution of one monomial here after change of coordinates only appears in monomials which are on the same face, right? So so now this group will be very important for us because it will allow us to define an intrinsic way of computing the invariant. Okay. So I denote by f and g the element of the corresponding to this map, just to introduce a notation. And then, in fact, this group, it can be decomposed as a semidirect sum product, sorry, so it's a semidirect product here. So there are two components. So there is a normal subgroup, which is G plus delta C. And there is another subgroup, G delta, which, well, I'm going to show in the picture. So the rightmost group, G delta, is something which acts only on the edge here. So it's simply given by this polynomial change of coordinates, where z goes to z plus some constant times x to the delta 1, y to the delta 2, okay? But of course here, I'm always supposing that this is a polynomial change of coordinates. So delta 1 and delta 2 are supposed to, in this context, let's say this map is non-zero if and only if delta 1 and delta 2 are positive integers. Okay. Otherwise, the group is just the identity. And so, and the second component, the normal component in the semi-direct product are let's say the change of coordinates which don't touch the main edges. Okay, so in fact it means that you see when you have let's say you see how the main vertex slides with respect to this second, the G plus component, they are edge preserving maps in the sense that there is no contribution to this rightmost edge, which appears that are denoted by E. Well, okay, so now there is this important definition. So among the adapted coordinate systems, there is one which we are going to call the stable system of coordinates. So what's stable? Yeah. So we start with any adapted coordinate system. So I recall this means just that it preserves the axis. And associated to this coordinate system, you have this the Newton polyhedron, right? So depending strongly in principle from X, Y, and Z. And I suppose that it lies on this class N, M, delta C. I recall delta C and M defines the affine plane which supports the main phase. Now, I say that X, Y, and Z are stable if for any element of the group acting on the phase, when you consider the Newton polyhedron with respect to the new coordinates, it lies on the same class. Okay. So what I mean by this is that the action of the group G delta cannot modify the supporting hyperplane. So if you recall the case of 2 dimensions, this is precisely the situation where, so in 2 dimensions, it's easier to see that what I asked you for is in the analog of this stability is that you could not displace the main edge by making such coordinate changes. But here, of course, is let's say that's 2-dimensional problem. So we ask to preserve the supporting affine hyperplane of the main phase. Okay. So yeah, so again, in other words, it means that you cannot make this phase move by the action of this group. And if this is the case, we say that we're in a stable situation. We are in a good coordinate system, which is stable. Okay. Now, so so later on, I'm going to show to you that it's always possible to find such a stable system of coordinates, which is moreover analytic. But what's the use of this? Of course. So one of this, the importance of using these coordinate systems is that using them, you can identify the final situations. So what I mean by final situation? Well, all the strategy is determined by the Newton polyhedron. So we'd like to identify in which situations we win, so in which situations we have achieved the elementary situation, right? So suppose that we have a stable system of coordinates, X, Y, and Z. Okay, so that's an important point. So if they are centered on the nilpotent point, then the following configurations cannot occur. So these are, you see, these are by the solid dot here. I mean the main vertex of the associated Newton polyhedron. Okay, so if the Newton polyhedron is in one of these 6 situations, we have already one, in the meaning that by which I mean that the corresponding foliation is locally elementary at the point P. Okay, why this is so? Because I recall to you that there is a criteria to show that a point is elementary, which was precisely to say that the Newton polyhedron should contain the origin on all possible coordinate systems. Okay, so you see that in all these 6 configurations, the origin is contained on the interior of the Newton polyhedron, right? But moreover, since we start with a stable coordinate systems, if you make any changes of coordinates in these configurations, because of the stability, you will always keep the origin inside the polyhedron. So by this, I mean that they necessarily correspond to cases where the 0 is inside the Newton polyhedron, and consequently, that the point is elementary. So these are the situations that we want to achieve by our procedure. Now, so most importantly, the use of this adapted coordinate systems, this stable coordinate systems, is that they allow us to define an intrinsic invariant and an intrinsic strategy of blowing up, which will not depend on the choice, on any choice, except for the global objectives which are given on the beginning. So I recall that the invariant is given by this six tuple of natural numbers, which depend strongly in principle on the coordinates x, y, and z. Okay. So first theorem, suppose that you have two coordinates x, y, and z, and x prime, y prime, and z prime, which are stable. So by stable, I recall it, I mean that I cannot move the face by this this face group. Okay. So in this case, I claim that the invariants given in one coordinate and in the other one coincide. So the six tuple of natural numbers coincide. Well, this is I mean, I'm going to give some ideas of the proof later, but so the invariants coincide, first of all, and moreover, and more important, the change of coordinates which maps x, y, and z to x prime, y prime, and z prime preserves the quasi-homogeneous filtration determined by the main phase. Okay, so not only the invariant, is preserved, but moreover, I recall too that the strategy of blowing up is determined by this filtration, right? So if I have a filtration which determines the blowing up in the coordinates x, y, and z, and in the coordinate x, y prime, z prime, they coincide. So using this result, we can define finally what we call the invariant at the point P. So we fix any arbitrary stable coordinate system at P, and we say that the invariant, let's say, of foliated manifold at this point P is simply the invariant computed with respect to these coordinate systems. Okay. So as I mentioned before, it does not depend, in fact, on the choice of x, y, and z. And secondly, the local resolution strategy at P is the weighted blowing up defined by the phase of the polyhedron, which is computed with respect to this stable coordinate system. So again, by the second part of the theorem, it's an intrinsic object. Okay, so now we have the two ingredients we have the invariant, and you have the local resolution strategy, right? So what we expect is to have the following result, which in fact we call the local resolution of similarity, because it says that locally at the point P, if you follow the local strategy, then you are going to improve the invariant, right? So you take this, this object, which now also, as I recall, depends, has the axis as one of its ingredients. And we consider now the blowing up at the point P. Let's say we germify everything at point P now. And we follow the local strategy, by which I mean I blow up the center. I make a weighted blow up of the center determined by the local strategy. And I denote by M tilde the resulting manifold, right? So now in this new manifold M tilde, I'm going to pull back all the data that I had from M. Okay, so I can pull back the divisor, the foliation, and also the axis. So I'm going to explain to you how to pull back the axis by this map. Well, as usual, the foliation, you just take let's say the total transform of the foliation, and then you factor out some power of the defining equation of the exceptional divisor in order to have something which is it does not contain components, nilpotent components of codimension one. And then the divisor, of course, the divisor is just the total transform of the preceding divisor, where you add a new component corresponding to the inverse image of the center by phi. Okay. So if you make this, I claim that.
Excuse me, Daniel.
Yes.
It's the blowing up that you consider here. It's sometimes a point, it's sometimes a curve, or it's just a point.
Yeah. I want to show you an example. Yes, yes. So depending on the position of the face, in some cases, the strategy determines a curve.
Yeah.
Okay? Which will also be given. It will be an axis. In fact, it will always already be rectified in this coordinates.
Okay, thank you.
So I'm going to show an example. So so for each point, so this should be a p tilde. Each point p tilde, which is on the inverse image of p by 5, and which is also important, we have that the invariant strictly decreases lexicographically. Okay. So this is the, let's say, this is all that we could expect. And it shows that if you follow this local strategy and you look at what we call the sequence of infinitely near points. So at each step, you look at just at the points which appear on the strict transform of the preceding step, you eventually will end with no nilpotent point because of this result, right? So, okay, now there's a second part. Of course, I'm not going to detail it, but we can show that we can globalize these local algorithms by the following reason. The reason that the invariant, as I defined here, is an upper semi-continuous function. Okay, so it means that at some given step, the strategy, now globally speaking, will correspond to the one of blowing up the locus while this invariant is maximum. Okay? And this means that if you make this blow up of this global center now and the whole manifold, and then you look to what happens in the resulting, let's say, foliation, you have some, this locus of maximal multiplicity will disappear successively. Okay. Yeah, so to answer to Fernando, this local center is always contained in the nilpotent lock. So this is some feature which is not, usually is not true in the usual resolution of singularities algorithms. As I mentioned to you, there's this case of the Whitney umbrella, where if you want to eliminate the pinch point, at some point you have to take the handle of the umbrella as a center. Okay, but if you look at the points which are not on, let's say, which are not on the origin on this Whitney umbrella, they are points of local normal crossings. Okay, so in this case, well, of course, for us, the normal crossings is the analog of the nilpotence. So I mean that in our strategy, this is the center is always contained in the better locus. Okay, so okay, so there, of course, the case where the center is the point, this is of course true because we are looking at nilpotent points, but there are two situations where the center are not local. I mean, the center are curves, and this corresponds precisely to these two situations, these two configurations of the main face. Okay, so the first configuration is the configuration where the main face has so the displacement vector of delta 1 is positive. So in this case, by the choice that I've made, if you recall, I've defined this derivative polygon, and I said that in this case, the main face should be the one which is vertical for which is the vertical, corresponds to the vertical edge for the derivative polygon. Okay? So if you lift this vertical edge of the derivative polygon to a face of the polyhedron, you get this face which is, let's say, somehow parallel to the screen, right? And now, of course, here you see that if you take the omega as a vector which is orthogonal to the hyperplane which supports this face, it should be at this part of this part, right? So there is a weight, positive weight omega 1 and omega 3, but a zero weight omega 2, right? So there is the y variables have weight 0 in these coordinates. So if you were to blow up with this weight corresponds precisely to blow up along this center. Okay. So the center now is just the y-axis. And okay, so it's easy to see that this center in this configuration is always contained in the nilpotent locus, because again, because of the characterization that I've given of the nilpotent locus as the points where the Newton polygon does not contain the origin, right? So if you look at what happens generically along this curve C, you see that when you take a generic point on the curve C, it corresponds to make this these dotted lines which appear on the drawing on the right leftmost side. So you see that for a generic point on the curve C, the polygon associated to this point, the polyhedron associated to this point, does not contain the origin. Okay, so all these points here are contained in the nilpotent locus. So the second configuration, which corresponds to the other axis, which should be taken as the center of blowing up, is this one, which is delta 1 equals to 0 and C equals to infinity. Okay. So in this case, the corresponding weight is given by this, okay, by definition. And then this corresponds to give, since we give weight 0 to the variable x, this corresponds precisely to blow up with weights omega 2 and omega 3 along the center given by the curve y equals to z equals to 0, which again is contained in the nilpotent locus. So the interesting thing is that the resolution, let's say this procedure, never touches points which are not on the nilpotent locus. Yeah, so now I'm going to show to you in a drawing how you transform the axis. So this is an important part because this axis, in fact, is what allows us to control the choice of local stable coordinates. And in some sense, this is one of the main points which, let's say, one of the main obstacles to generalize this procedure to higher dimensions. Okay? Because they do not behave so well in dimension 4 and higher. So what we do, you see that there is this axis. I recall to you this axis is something, is some one-dimensional foliation is somehow transversal everywhere to the nilpotent locus of the foliation F. So now we suppose that we blow up locally with the center, which is prescribed by the local strategy, as I recall here. And then what happens to this axis? I claim that when you take the strict transform of the axis by this blowing up, you get an axis for the new triple M tilde and E tilde F tilde. Okay. So I recall that an axis should be satisfied that those requirements, saying for instance that it's not singular, right? So it's axis. So what happens here? You see, you take let's say like here in the left, you have the axis in the original coordinates. So these are given by these vertical lines, the vertical dashed lines here, right? So it's a regular foliation. There is no singularities. And now we blow up the point P, right? So with the strategy which is determined by the algorithm. But when you blow up a point and you look at the pullback of a regular foliation, you necessarily introduce singularities. Okay, so you see here that they appear here. So there is one singularity here, which is of saddle type, and one singularity here below, which is also of saddle type. Okay? So in principle, if in these 2 points, you no longer have an axis because the foliation given by calligraphic A is singular, right? But recall that, so these points, there are 2 singular points in the inverse image of the foliation, which are the points given by let's say, if you think of this as a sphere, they are given by the North Pole and the South Pole of the sphere, right? But fortunately, these points are no longer in the nilpotent locus. Okay? So in fact, you don't have to take care of these points, because precisely our algorithm, I'm going to show you a drawing in a moment, show that these points here are already elementary for the foliation that I want to simplify. Why this is so? Well, I have to recall to them how this blowing up acts by, like, geometrically. When you look at its combinatorial action, you see that you have this face F, and when you blow up in the Z direction, let's say you look at what happens locally in the two poles, the North Pole and the South Pole, it corresponds to this projection here, right? So you just project the face on the horizontal plane. But you look at, it's very easy to see that in this case here, you end up in a final situation because the vertex now is at the origin. So by this, I mean that in these two potentially problematic points, sorry, yeah. So in these two potentially problematic points, in fact, you don't have to define an axis, because they are points which are not in an important locus. So the strict transform of an axis is an axis. So again, this is the data that you're going to pull back to define a new invariant, which allows you to prove this the reduction of the invariant, okay, with respect to the strict transform of this previous axis. Yeah. So I think I'm going to detail this a little bit later, but just to explain to you how to achieve this stabilization, right? So we recall to you that to measure our invariant, we need to be in a stable coordinate system. So now I explain to you why I have split this. So we have this group which acts on the face. I noted G delta C. And I said that I have a splitting of this group in a part which acts on the edge, and a second part which acts, in fact, on the face minus the edge. So why I have this splitting? Because now the stabilization of the face, I mean, the choice of you start with any adaptive coordinate system, and now the stabilization goes as follows. First of all, I've drawn here in this by this line M delta. This is the edge, let's say the rightmost edge of the main face, the edge which corresponds to the connection between M and M prime, where M prime is the main vertex of the derivative polygon, right? So now you have this edge, and the group which acts on the edge is the group which I call G delta. Okay, so this group which just corresponds to a sliding along the edge, right? So the idea is the following: if the edge is not stable, right? So there is a map of the form that there is a map of the form that I showed before, which will move this edge. Okay? So whenever it moves this edge, it will make what will appear is an edge which is still a little bit farther, right? So there is two ways where an edge can be farther away in this case, either by, let's say, by going to infinity in the way that I show in the first case, or in the second case. Okay. So in the first case, I claim that the reason is by contradiction. So we suppose that there is no finite number. There is an infinite number of steps in this preparation, such that at each step you are able to eliminate the main edge by the action of this group, right? So, okay, so this procedure formally converges to these two situations, we can say, right? So in this first situation, when you see what happens to the polyhedron at the limit, you have a polyhedron which is written now in a formal system of coordinates, which has, let's say, which it's situated above a hyperplane, let's say a hyperplane determined by the height of the main vertex. Because everything which is below the main vertex will disappear by this formal sequence of coordinate chains. Okay? But as we have seen, this cannot happen because if this happens, it would imply that in this formal coordinates, the z plane would be inside the nilpotent locus, and this is not possible by the hypothesis, because it's supposed that the nilpotent locus has codimension greater or equal than 2. And so there's this, so there's this second situation here where you have this limit, right? So there's a limit where, let's say, then you stabilize the first coordinate at some height a, and then it goes at infinity on this way, right? So this can happen. And in fact, what we show is that when you have a limit, a formal limit, which happens in this way, okay, by an argument using a faithful flatness, then in fact, the formal change of coordinates, which allows you to pass the limit, gives you an analytic change of coordinates. Okay. So this because, in fact, this is because we started an analytic object, and you can formulate the existence of this configuration as, let's say, some relations between the coefficients of this analytic, the analytic coefficients of the vector field. And in particular, there should be, if there's a formal way to, if there is a formal way to achieve this limit here, then there is an analytic way to achieve this. Okay, so this is for the edge stabilization. So by up to a finite number of steps of the action of this group G delta, of course, G delta changes each time that the displacement vector delta changes. But at some point, you get a situation where you cannot move anymore this main edge by the action of G delta. And then I achieve a preliminary situation where which I call edge stable situation, right? Now, I proceed by assuming that I have stabilized the edge, and now I'm going to stabilize the face, right? So now, using the direct sum decomposition that I explained before, I'm going to make, I'm going to study the action of the second part of the normal subgroup given by the maps, which preserve the edge, because I don't need to touch anymore the edge. I only need to touch the parts which are of the face, which are, let's say, to the left of the edge here, right? So you see that again, there can be some movement if the edge, if the face is not stable, but the edge is stable. You can still have this movement here, which I've drawn in the rightmost side. But again, by this argument of faithful flatness, you can prove that if there is an infinite number of movements which appear like this, so at the limit, you are going to converge to a situation where you see that the face is a parallel. Let's say the face is let's say it's parallel to the x-axis, and in this case, it corresponds again to a situation which can be achieved analytically. You see again, because, well, let's say just to give an intuition, when you achieve the situation formally, it implies that the x-axis is inside the nilpotent locus. Okay, and this, if it's formal, if it's a formal curve which is inside the nilpotent locus, it should be analytic. Okay? So by which I mean that you are in this situation that I showed you. Okay, so this is the situation where this is one of the limit situations, and it corresponds to the case where the axis, the center for blowing up is given by the axis. Okay, so I'm going just to conclude by giving some words about the. Yes, so that you recall that in this case, I've told you how to treat the points which are inside the divisor, right? But I said that this is the typical situation, by which I mean that, let's say that the divisor plays an important role because it allows us to redefine the change of coordinates as much as the axis. But if you are outside the divisor, so of course you can have curves of singularities, which are, in particular, when you begin your resolution algorithm, there is no divisor, right? So how do you deal with the points which are outside the divisor? So now is the idea of globalization, which let's say that which appears already in the works of Felipe Cano, which is the following one. If you are outside the divisor, then the generic points. So if you have a curve of nilpotent points, this curve is generically equidesingularizable. By which I mean that except for a finite number of points, let's say a discrete set of points in a curve, the algorithm of resolution can be given uniformly on each point. Why this is so? Okay, so I'm not going to detail too much, but okay. So let's take the situation here, right? So you have this vector field. Yeah, okay. So this is typically, if you recall, I've studied this example several times. This is typically the case where you have an nilpotent singularity at the origin, right? But now you have three variables. So you have x, y, and z. But the vector field itself, it depends only on z and y. So by which I mean that if you draw the Newton polygon, the Newton polyhedron in this case, you have something which has a form of product, right? So there is no dependency on x, which means that the curve given by x equals to z equals to 0 is equidesingularizable, right? So here you can desingularize all points on this curve at the same time simultaneously just by blowing up the curve C with the weight given by this graduation, right? So, I mean, in this case, you see that this curve, in fact, the resolution of singularities along this curve reduces itself to a two-dimensional problem, right? So, in fact, if you consider this situation and then you put some, let's say, some higher order terms which do not contribute to the main phase, so you can see the perturbation of this by adding terms which are, let's say, above this plane, the same thing will hold, right? So this is a completely stable, let's say, robust situation. Now what happens? So now suppose that you have this situation, but you add this function f here, right? So this function f, let's say something of the form f of x is equals to x to the power k, right? So now this curve is no longer equidesingularizable, because there is a point at the origin which is more complicated than the rest, right? So this, in this case, I've drawn let's say the Newton polyhedron at the origin, and you see that in this case the algorithm at the origin is not the same that you would achieve on a point where x, let's say a point on this curve where x is different from 0. But fortunately, let's see what happens when you take, let's say you just make a x, sorry, you make x non-zero here, right? So you have exactly the same situation as before, which corresponds geometrically here to project this point here, right? So in fact, this curve is equidesingularizable except for the point x equals to 0. So in fact, when you place yourself along a nilpotent curve which is inside the nilpotent locus, in some sense, this happens, you can characterize completely this kind of situation by saying that except for a number of, let's say for a discrete set of points, you always have an equidesingularizable situation. Okay? So the preparation, let's say, as recall that I said in the two-dimensional case, I'm going to finish, you have this preparation which corresponds to include the nilpotent locus in the divisor. Now, the preparation that we're going to make before applying the algorithm that I explained consists in the following one. You take all the points in the nilpotent locus, right, which are not equidesingularizable. So this is a finite number of points in each compact, let's say, in each relatively compact component. Because as I claimed to you, if you place yourself along each curve, each is equidesingularized except for a discrete point. So these points you can somehow artificially, well, you can include them in the divisor by blowing up with a convenient weight. And then, let's say, we can say that the points which are not equidesingularizable are inside the divisor. And for them, we apply the algorithm that I explained before. And for the points which are are in the equidesingularizable locus, we reduce the problem to a two-dimensional situation, as I explained. Well, I think I'm going to finish here, but next time I'm going to explain, well, why these ideas don't work for higher dimensions. And I'm going to try to explain to you some new approach, which for, let's say, in my point of view, it's more conceptual. And in some sense, it prevents all these problems which are caused by the existence of this. So there's a lot of problems which are caused by the existence of these points with negative indices, right? So this is why this invariant is so complicated. So I'm going to explain to you that there is a new approach that it's a work in progress that I hope will somehow deal with this problem. And in fact, deal with much more general situations where you don't consider just vector fields, but hopefully, if things work, you can desingularize any differential operator of arbitrary order.